So I only have like 10 minutes, so I will rush. Okay. Okay. So hi everyone, my name is Thong, and today hopefully in 10 minutes I will talk to you about the phenomenology of dark matter in compact object. And it's not just one paper, it's actually 3 papers in 10 minutes. One paper we already published with my collaborator, also my master advisor Tim Tay, and another 2 is working with Tim and my PhD advisor at Stockholm University, Tim Linden, and Julie from Liverpool University, and Joe and his wonderful group in Nguyen University and Barry Peter Institute. So the outline of this talk is first, and we talk about how the compact object like star in our Milky Way galaxy can capture dark matter, or you can buy it on Amazon. The second one is after the dark matter is captured, it can either be collapsed or it can annihilate or reduce some signal, and when we can detect it in neutrino and gamma ray experiment. So one of the simplest idea of how the dark matter can be captured by compact object is consider like an arbitrary star made from like nucleon or something, and then the dark matter can come in with initial velocity, and after it's scattering with a nucleon inside the star, then it can lose kinetic energy and be captured by the star. So the quantity to demonstrate how much dark matter capture in star is the capture rate, and in here I show you just like a formula for the capture rate, and you just need to notice that this formula it depends on the dark matter density, which we consider for different dark matter density profile. And also it depends on a variable called optical depth tau, which is a fraction between the cross section of dark matter with nucleon and the cross section of the geometric cross section of the star. So in here you can see the calculation. First, it depends on the dark matter model, and second, it depends on which star you choose to consider. So the first scenario, which we are investigating and will publish on in another paper, that's if after the dark matter capture, and then it can thermalize inside the star, and it can collapse, and when the dark matter somehow like forming some kind of like a subhalo in the star, and this radius like crossing the structure radius, then it can become black hole, and then the black hole consume the star, and then boom, right? So this kind of scenario can lead into some astrophysical signal like neutron star merger, gravitational wave, and especially the fast radio burst, which we consider about. So another scenario is the dark matter. Actually, it's already covered a little bit in Natsumi-san talk. Is the dark matter can hit in the star, like Joe used to say that you can do barbecue on the star. So first it can do like kinetic hitting, and the second one is can like the dark matter got trapped inside the star can annihilate to reduce some standard model particle, and then those can also hit in the star. But in here I want you to focus on this second scenario, the annihilation one. So instead of like we bombard to proton collider, it's CERN, we use neutron star to bombard to dark matter particle inside the star. And after the 2 dark matter annihilate inside the star, if it can produce some kind of like long-lived particle, like some kind of Z prime dark photon, it can escape the star and decay into neutrino or photon, and when we can calculate the energy flood from the process. And this flood it depends on the energy spectrum, which depends on the rosette you choose to consider. And then you can detect them using iScope or Fermi telescope, blah blah. So which dark matter model we choose to consider, right? So if you Google like all of the dark matter model, you can find the Venn diagram made from Tim, very famous diagram. But we choose to consider a very simple model, and we want our mediator have to be very light, so it can have long life and escape the star. So we choose the dark photon model, which I think is covered most on Takumi-san talk. So the dark photon model we use to consider it very simple. We just add another U1H hypercharge group in here, and we add another dark matter candidate, fermionic dark matter candidate, and then dark photon mediator, also a kinetic mixing term. So in here you can see that the dark matter can interact with the standard model directly through a dark photon, or it can mixing with the standard model, photon or zero zone, and interact with the proton or neutron. So we first we consider like the case where the dark photon decay into two neutrino. Then we want to know like is I group or infrared can detect those flux. So in here I show the limit from I group from and infrared, and also I show the limit, the projection limit from area collaboration. So and I plot all the horizontal line in here. Is these line are the maximum flux we can get from this scenario, and you can see, yeah, no current experimental limit can constrain somehow your the dark photon model. So so here's our money plot. So first one the y-axis is the cross section, is the spin independent cross section of dark matter with nucleon, and the x-axis is the mass of the dark matter, right? So in here the direct detection which already covered by Kieran first lecture, and first we input the classical Navarro friend white dark matter density rho phi, and we take into account to all of the neutron star in our galactic center, and we use ice group, so we can constrain a very tiny little bit of the cross section here. But if we change the dark matter density rho phi, so we add more dark matter near the galactic center, so we can constrain a lot of, we can have the bound from TeV to near to PeV for the cross section. And if we do the same for the raw data from ice group, also we can have go further like 10 to the 7 GeV, and we can push the limit down to 10 to minus 46 centimeters square without using a direct detection. And then again, I put the projection from area to show the potential of area to exclude a lot of parameter phase space of the super heavy dark matter. So another thing in here, and you can see that these bounds are very dependent on the dark matter density rho phi inside the galactic center, and we don't know what exactly it is. So if in the future we detect some kind of like dark matter in here, we can have some information of the dark matter density rho phi in the galactic center, right? So the ongoing work with me and two teams. In here, so we consider a very specific case that the dark photon mass is very small, very small, and from the effective filtering point of view, you can like integrate out all the heavy field, and you have the Euler Heisenberg Lagrangian, and you have the model you put in Fayou, and voila, you have this type of coupling. So you can have one dark photon decay into 3 photons. We write a model, we did a calculation, and we compare our result with the God of dark matter post-Popelov, and we see that our result is agree with him. And also we write a code to boost the plot into arbitrary frame, and so right now we have the plot already. Now we just run the data analysis, and we have the result in preparation. So why do we care about this rosette? Like it's very small, like one dark photon can get 3 photons. First one, we want to constrain on the low mass regime of the dark matter. We hope we can get some bound here because Fermi and Hawk can have some limit in the low mass regime. 1 minute, okay. And the second one is I stole this plot from Kieran. Is we hope from this guy of rosette we can put some constraint, put some color in his beautiful plot in here. So maybe it's here and here. We hope so. We don't know. So yeah, so that's our motivation. And the take home message of this talk is I just sum up in one quote is by looking at the star, looking at astrophysical signal, we can actually study something about the dark, the particle model. And I leave you with my favorite candidate, dark matter candidate, the dark matter. So thank you for attention.
star distribution in the
Okay. It's like I pay you money to ask me that. I prepare a slide. So yeah, so we use some kind of simulation, the neutron star simulation number density in galaxy center, and this simulation they get it by integrate out of all the electron density in galaxy center. They have some profile, some observation for it, but the reason this question is very interesting is because, as you can see, that this depends a lot on all the neutron star number density, right? So the most astrophysical fluctuation is from here. So in the future, if we have better measurement, the better simulation, we can reduce the statistical uncertainty. But right now, we're just using the simulation.
Okay, then let's thank Thong